Hello and welcome to Advent of Code. We have day 16 here. So this was a problem that I had to skip for a day, but I thought we might try to tackle it at maybe a more leisurely speed and hopefully produce a better answer. So yeah, let's talk about the problem a little bit. I've looked at part one, but I don't know what part two is yet. So we'll see how that ends up looking. All right. So what we have here, 16 programs in a line. They're all named A through P. So we might start with something like a sequence of all the letters in the alphabet. K, L, M, N, O, P, like this here. And if we wanted to make sure that we didn't miss any, we might do a count like that. And I think it might be useful to have a vector of these because of the operations that we're expected to do on them. And there's three operations that we're expected to do. We can take a quick look at our puzzle input to get an idea of it. But it seems here like comma is our delimiter. I'm going to say this is day 16. So comma is our delimiter, and it seems like the first character is the one that sort of determines what we need to do. So if we had perhaps our day 16 here, and then this is something that we went and split by commas, for example, then we'd wind up with a sequence of instructions. Seems like it might be a further more reasonable thing to trim what we slurp out here so that we don't have that new line at the end. Okay, so yeah, so we might define a function here, dance, with our dancers and the move that they have to do. And yeah, the move as it's coming in seems like it's going to actually consist of maybe something that we might call like M, and then something like the rest of the move. Let's say something like this. So far, we got the spin, the exchange, and the partner. So all right, let's try talking about spin first. So we might use like a case statement. I think here works pretty well. So we can say that if it starts with the S character, then we know that we need to do a spin. So we need to sort of turn the rest of move here. Will this work? I think because of destructuring, it might not. So let's just do this here. So here, we'll have our number n, the number that we have to sort of spin the dancers forward, and yeah, so it looks like, based on the example that they provided, that that spinning forward means sort of spinning to the right. So in order to spin to the right, I think what we can sort of do is we can make a cycle of the dancers, and then do something like drop. Let's see. So we can sort of subtract from the number of dancers that there are. We can subtract this number n and produce a vector of the results, something like that, and then verify that. So I think that so far they're asking us about. So if we talked about having, let's say, a vector of these, and we knew that the next dance move was S3, like this, then it would seem like, well, that's interesting. Oh, of course, because it's necessary that we only take the the right number of dancers from this. Okay. All right, and in this case, CDEAB, which is in fact the right answer here. Okay, so it looks like we know how to spin. What's the next thing here? It's exchange. All right, so it starts with an X. Then we sort of have to talk about, let's see, the programs at positions A and B. Okay, so yeah, we might reconstitute this string here and then do something like our regex match on. Well, let's see. It's going to be something followed by a slash followed by something else. Dot star. That seems pretty good. And then we can let maybe our A and B here be the rest of the regex match, just because of the way that regex match returns the whole match followed by individual groups. So now we have A and B in the positions, and now we just need to exchange them here. So we can sort of, I would think, take our dancers and then do an update on them. Update or assoc. Assoc is probably fine. So for the dancers, it seems like we want to associate in position A whatever is in dancers at B, and associate in position B whatever is in dancers at position A. And yeah, this looks pretty good to me. So if we're talking about doing the dance, and we wanted to say exchange, let's say 0 and 2, no matching clause X, unable to resolve RE matches. Okay. Key must be integer, it says. So what's going on here? Oh, I think it just needs us to turn these strings here into integers. And here we've swapped A and C. So this looks like the right behavior to me. All right. Then finally, we have partner. The program's named A and B. Swap places. So it starts with a P. Then I think we want to start in a similar kind of way. We don't need to actually read the string. We can take this part out. But we do need a way to sort of look up these values in dancers. So I think we can make use of Java's index of here. Something like this and this maybe. And then just maybe to make sure that we're not shadowing anything unexpectedly. So here we've looked up the location of the dancers. And now we just need to say that we want to swap them. All right, and then this should be an implementation of partner. Let's see, B, okay. All right, so then if we want to swap A and C here, it says key must be integer. Okay, good to know. Let's see. So I think, right, of course. Partners. Okay, now we have an index out of bounds exception. That's interesting. So I think that what is going on here is that actually we probably don't want to do a regex match here because we know that these are just going to be 2 characters. So I think we want to do something like this. Basically saying we know that move is going to consist of a dancer, a slash, and then another dancer. And then in this situation, okay, very good. And if we want to switch, let's say B and E, very good. All right, now we have a puzzle input, which we've already saved. And we need to start with this here, and then we say something like just reduce based on dance, starting in this state and working over the split based on commas. What we got here, okay, and then it's asking in what order are the programs standing. Okay, so let's apply stir to this so that we can get something that's easy to copy and paste. Okay. So tentatively, this looks like pretty good input. Doesn't seem like any characters are repeated. All right, right answer. There's our gold star. All right, second half. Let's see. Get a feel for the dance moves, the dance as a whole. Okay, keeping the positions they ended up in from their previous dance. The programs performed again and again, including the first dance, a total of 1 billion times. Okay, so let's see. So their second dance would begin with this order. Okay. After their billion dances. Interesting. Okay. Well, so I guess the naive way to do something like this would be to put a repeat in here. Repeat 1 billion. And kick something like this off. Ooh, no matching clause. Okay. Let's see here. So the issue here is that this, let's see, this thing, this is a collection, so you can't call repeat on it. We could, okay, so it is a collection. So actually, I guess we can call repeat on it. It's just that then we have to apply concat to it. Okay. All right, so kicking that off, but then we might also want to ask the question of how fast are we switching through these kinds of things. So we can put like a timer around this thing and say something like, oh, let's see, we just did repeat 100 times. Well, this doesn't seem very promising. Let me cancel this. How about just a repeat once? So, all right, so this did produce the right answer. Okay, so the problem seems to be that the implementation that we've used is linear and slow. All right, so let's see. I wonder where most of the time is being spent. Yeah, if I had to guess, then I would say probably around the actual vector operations here. So it would be good to have a more efficient representation there. Yeah, yeah, I would say something like that. So yeah, tentatively this takes. So that last one took 2.7 seconds, and I'd expect this one to take almost 30 seconds, and that's only repeating 100 times. All right, let's see if in what order are they standing after their billion dances? Yeah, it's a very good question, and it makes me kind of curious about what I would just like to look at real quick is if I repeat this once, twice, and 3 times, if there's perhaps any useful pattern here. So let's see. Yes, actually, it does make you wonder, because it does seem like there's a certain sense that the operations can maybe be collapsed so that they don't all have to happen, that maybe they don't all have to be executed. Like, for example, if there was a shift right followed by a shift left, then there's a sense in which those could be sort of ignored, maybe. Or if you're swapping the position of two dancers, that it could sort of be ignored, if the only thing you were doing after that was swapping other dancers. The other option is to do things more efficiently, but I at the scales that we're talking about, that doesn't seem too particularly feasible. Okay. Yeah, I think we're fine just stopping this. No need to waste CPU cycles on something that's never going to finish. All right. So, how about we look at these the contents here? Maybe it's the first 5 things. So, switch the things that are at this position, then partner up these two, then do a shift of 10, then switch the things at these positions, then do a partner of these two. So I wonder if doing a partnering can just be completely ignored in a certain sense, because the partner swapping can all be done. It can all be done like at the last minute. Yeah, I don't see any sense where a partner swapping is actually going to be connected to the actual problem. So I think we might change the definition of dance to only include these 2 cases, and then do something like a filter, maybe like starts, or like a remove everything that starts with T to be like the input here, and try like doing something like this. And then I guess in another REPL, we would want to try something that's potentially a lot faster. Is it faster? 1 second. So it looks like it's going to take more like 10 seconds here. Yeah, not only that, but it also seems like the way that I changed the implementation isn't so great. Well, so the thing about the spins and the exchanges is that it seems like you can't really take them out in the same way that the p's are sort of all combinable. Um, hmm. Hmm. Well, maybe there is a sense in which the s's and the x's are combinable, basically in the way that you can figure out what x is supposed to be by keeping a track of how many spins have happened so far. So if we had like some kind of dance 2, for example, maintaining some kind of dances state. Okay. And the same general structure here, but producing something maybe a lot different in each of the implementations. Okay. So the dances here sort of are going to consist of like the spin number, the exchanges, and the partnerships. Okay. And then in a partnership, so this is the easy part, we're just going to pull out those values A and B and cond into the partnerships this AB value here, leaving spin number and exchanges the same. Then in a spin, we'll pull this value out. And yeah, to this, we just basically want to add to the spin number, the number n here, leaving the exchanges and the partnerships the same. And then in an exchange, so this is maybe the trickiest one, we want to say that the things that need to be exchanged are, so leave the spin number the same, leave the partners the same, but the thing that needs to be exchanged is conjoin onto the exchanges. The numbers are going to be basically add to A, the spin number, and add to B, the spin number. Like this. All right, so now in this situation, with the definition of dance 2, yeah, what would happen if we called it on, like, say this with a list with a spin number and an empty number, exchanges an empty number. Okay. No matching clause P. Okay. Okay, so this says basically just swap B and E. Okay. All right, so if we define DD to be something like, we need this part here. And then we say something like reduce dance 2, starting with 0 to empty lists like this. Will this, let's see. So, Okay, take this part out. This is from an older thing. So this should finish pretty quick. Okay. Now, how about this part? 1 million part. This a couple seconds. This might not also work. Or rather, this might also be not enough. Okay, let's cancel this right now. Let's talk about what happens when we just run this once. So here is, so what are we talking about here? The first element is the spin number. The second is the thing of the things that are being exchanged. So about this, okay. Okay, these numbers are being exchanged. So so I guess this number that we're tracking here really only has to be the remainder of, let's see, the count through P. So 16. So this. Okay. And then I guess the spin number can also be talked about in the same way. All right. So, So yeah, I guess I'm wondering. So the spin number I think is pretty good, and each of these I think can kind of be collapsed. So if you know that 13 and 12 and then 15 and 13 are going to get swapped, then you know that 12 and 15 are going to get swapped. And and yeah, it seems like so what was in 12 becomes in 13, what was in 13 becomes in 12, and then was in 15. What started in 15 ends up in 12. And oh no, that's not the case. It is the case though that what started in 12 does end up in 15. What started in 13 ends up in 12, and then what started in 15 ends up in 13. Okay, so there's a sense there. Okay. So I think that's the right approach. But I'm keeping my eye on the clock, and the next problem is going to be dropping in about 5 minutes. So I want to make sure that I got enough time to give that a good crack at it. So I'm going to take a pause here and get back to it either after this problem or tomorrow, depending on how time works out. But I'll see you in about 5 minutes. Thanks for watching.